Good evening, everyone. I am NP Raju, faculty at ACE Engineering Academy. I have been associated with ACE Academy since 2014. I have 13 years of teaching experience. Today we are going to discuss significance of ideal gas analysis in thermodynamics. So in thermodynamics, ideal gas is extremely important because 80% of the syllabus is based on ideal gas. So that is the reason we need to see what is ideal gas, what is exactly ideal gas, under what conditions gas behaves as ideal gas, what are the examples of ideal gases. All these things we are going to discuss in detailed manner. And today I am going to discuss what is working fluid and what are the various examples of working fluid, what is difference between gas and vapor, what is ideal gas, and we will be seeing kinetic theory of gases. Some points I will be taking from kinetic theory of gases, and when a gas behaves as ideal gas, and what are the examples of ideal gases, and what is perfect gas. All these things are extremely important in thermodynamics. So let us begin with working fluid. What is working fluid? It is a fluid on which the thermodynamic analysis is done. That is called working fluid. It is a fluid on which thermodynamic analysis is done. This is called working fluid. The fluid on which thermodynamic analysis is done, it is called working fluid. And what are the examples? What is the meaning of working fluid? Suppose if you take IC engine, internal combustion engine. Suppose in case of petrol engine, air fuel mixture will enter. During suction stroke, air fuel mixture will enter. So when spark is given, the combustion takes place. During suction stroke, air fuel mixture will enter, and compression stroke, air fuel mixture is compressed. When spark is given, combustion gases are produced inside the cylinder. Combustion gases are produced. These combustion gases expand on the piston. When the combustion gases expand on the piston, therefore the piston moves, thereby work is produced or power is produced in IC engine. So therefore, the combustion gases or simply gases is working substance. Simply the combustion gases or gas is working substance in IC engine, because this fluid, this gas is producing power. So that's why it is working fluid in case of internal combustion engines. Suppose if you take steam turbine, steam is working fluid in steam turbine. In gas turbines, gas is working fluid. If you take steam turbine, suppose there is a turbine, this is inlet section and this is exit section. In case of steam turbine, steam enters into the turbine. So inside turbines there are blades. So when the steam expands over the blades rotate, thereby the shaft is rotating because the shaft is mounted on the blades. Therefore, when the blades are rotating, shaft rotates, thereby turbine is producing work output or power output. So since the steam is entering and producing power output, steam is working fluid in steam turbines. Similarly in gas turbines, suppose if this is gas turbine, gas enters, again combustion gases only, combustion takes place in combustion chamber. In gas turbine power plant there is a combustion chamber. In combustion chamber, combustion takes place. From the combustion chamber, combustion gases are simply gas. The gas comes from the combustion chamber, expands over the turbine blades, thereby turbine rotates and it develops power. In steam turbine, steam is working fluid. In gas turbine power plant, gas is working fluid. So this is working fluid. The fluid which is used in the thermodynamic analysis, or the fluid which develops power. In case of IC engine, combustion gases. In case of steam turbine, steam expands, or gas turbine, gas expand, this is working fluid, right? But what is difference between gas and vapor? Because if you see the entire syllabus of thermodynamics, if you observe carefully, there are only two working fluids, that's all. Either the working fluid is gas or the working fluid is vapor, that's all. 80% of the syllabus, the working fluid is gas only, that is ideal gas. And remaining 20% of the syllabus, the working fluid is vapor or steam vapor. Vapor means it is steam vapor. So first of all, let us see the difference between gas and vapor. Just we are going to discuss the definition. What is gas, what is vapor? Just I am going to give the definition. Suppose vapor. If the temperature of the substance is less than its critical temperature, it is gas. The temperature of the substance, if the temperature of the substance less than its critical temperature, if the temperature of the substance is less than its critical temperature, it is vapor. It is a just definition only. It is just definition. Suppose if the temperature of the substance is greater than its critical temperature, it's a gas. Temperature of the substance greater than its critical temperature, then it is a gas. It is just the definition. What is gas, what is vapor? It is just definition only. Suppose, if you see this diagram, this is temperature and entropy diagram. And this diagram actually we study in properties of pure substances. Actually, this is saturated liquid line, this is saturated vapor line, this is liquid region, it is liquid plus vapor region, and it is vapor region, or sometimes it is superheated vapor region. So this point is known as critical point. This is saturated liquid line, this is saturated vapor line. Both lines meet at a particular point. That point is known as critical point. This concept actually we study in properties of pure substances, but for the time being, I am taking this diagram because for the discussion of the gas and vapor, just now I have given definition only, but what is critical point, what is critical temperature, what is critical pressure, actually we study in properties of pure substances. But anyway, just briefly I give this concept because definitions are based on properties of pure substance only. So this point is known as critical point. This is critical point. At critical point, there is temperature, that is critical temperature. Suppose at this point, there is some temperature. So at this point, this is temperature axis. At this point, there is temperature, that is critical temperature. And the definition, according to the definition, if the temperature is less than critical temperature, so here this is critical temperature, and if the temperature of the substance is less than critical temperature means this is the region, less than critical temperature. But this is vapor region, please observe. This is liquid region, this is liquid plus vapor region. So you remove, you don't look at this here. This region don't look at. In this region, if you see, this is vapor region. Less than critical temperature, this is vapor. The definition is if the temperature is less than critical temperature, this is vapor region. If the temperature of the substance is greater than its critical temperature, this is critical temperature, greater than critical temperature, in this region it is gas. So that is the difference between gas and vapor. So this is critical point. Below this critical point temperature, this region it is vapor. Above this critical point, this region it is gas. But actually, what is critical point? Full details you study in properties of pure substances. Just it is a definition. Whatever just now I said, it is just a definition only. So we need to discuss so many things in properties of pure substances. We will be discussing what is saturated liquid, what is subcooled liquid, what is saturated mixture, that is liquid plus vapor mixture, or it is also called wet steam. what is saturated vapor, what is superheated vapor. All these things actually we study in properties of pure substance, but it is a just definition, right? It is a definition. So this is the difference between gas and vapor, but actual things you study in properties of pure substance, right? Just I have taken definition only. Now, atmospheric air. Just now I have given what is working fluid and examples. What is gas, what is vapor, just definition only I have given, right? Next, atmospheric air. Suppose there is a container. In this container, there is atmospheric air. We have taken some air, atmospheric air in this container, or suppose in your room there is atmospheric air. Suppose you are staying in one room, you are sitting in one room, in that room there is air, suppose there is air, that is atmospheric air. So there is a thermometer. We kept some thermometer. Suppose this thermometer is giving temperature. Suppose this temperature is 25 degrees centigrade. This thermometer reads, suppose 25 degrees centigrade temperature. Actually, this temperature is temperature of air. That is nothing but atmospheric air only. This air is nothing but atmospheric air only. So temperature of air is 25 degrees centigrade. But what is actually air? What is actually atmospheric air or simply air? It is a mixture of different gases. It is a mixture of different gases. Air is mixture of different gases. Oxygen, nitrogen, CO2, helium, argon. There are so many other gases. It is a mixture of oxygen, air is mixture of oxygen, nitrogen, CO2, helium, argon. There are so many gases. It is a mixture of different gases. Air is mixture of different gases. This temperature of air is 25 means, but here this air is mixture of different gases. Suppose in this container there is oxygen and also there is nitrogen. Suppose what is the temperature of oxygen? And also suppose what is the temperature of nitrogen. And you remember, in this room, you are measuring some temperature of air. If that temperature of air is 25, each gas is also will be at the same temperature. Try to understand. It is a mixture of different gases. Air is mixture of different gases. You are sitting in the room in which there is air. This air is mixture of different gases. If the mixture temperature is 25, each gas temperature is also 25 degrees centigrade. Oxygen will be 25 only. Nitrogen will be 25 only. Helium will be 25 only. CO2 will be 25 only. Each gas is at the same temperature. In this room, if temperature of air is 25, each gas is also same temperature because it is a mixture of different gases. Each gas is also at the same temperature. Oxygen temperature is also 25 degrees centigrade. Nitrogen temperature is also 25 degrees centigrade. Similarly, each gas is also at the same temperature. So it is an extremely important point. If the mixture temperature is 25, each gas is also at the same temperature, right? Right. So this is atmospheric air, right? Now, let us see the critical temperature and pressure for various substances. Now I am going to give a table just for idea, for examination point of view, for GATE examination or engineering services examination point of view. These values are not required, just for idea I am going to give. Suppose there are some substances. Suppose there is air, oxygen, nitrogen, hydrogen, helium, and argon. These are some substances, suppose. And critical temperature, degree centigrade, and critical pressure, kilopascal. So for these substances, I am going to give critical temperatures. For air, the critical temperature is minus 140 degrees centigrade, oxygen minus 119 degrees centigrade, nitrogen minus 147, hydrogen minus 240, helium minus 268, argon it is minus 113. So these are critical temperatures in degrees centigrade for these substances, just for idea, not required for any examination. These are practical values, just for idea, right? Critical pressures, suppose air, it is 3700 kilopascals, oxygen 5000, nitrogen it is 3200, hydrogen 1300, helium 227, and argon it is 4870 kilopascals. These are in kilopascals. Just for idea I am giving, just for idea only, no need to remember these values. What is the significance we will be seeing, right? So this is the critical pressure and critical temperature values for these substances practically, right? Now, just now I said, if actual temperature of air is 25 degrees centigrade, each gas is also at the same temperature, I said. Oxygen 25, nitrogen also 25, very good. And also just now we have seen, what is gas, what is vapor, just now have given. What is gas? If temperature is greater than critical temperature, it is gas. If the temperature is less than critical temperature, it is vapor. Just now we have seen the definition. Now, look at here. If you see air, actual temperature of air, if you take air, what is actual temperature of air in the room? Actual temperature of air in the room is 25 degrees centigrade. Just I have taken roughly 25. You take 20 degrees, you take 15 degrees, or you take 10 degrees, or you take 30, 35, 40. Roughly, I have taken 25. Roughly. So actual temperature of air is 25. But what is actually critical temperature? Critical temperature of air is minus 140. Now you compare actual temperature of air and critical temperature of air and tell me which temperature is more, actual temperature is more or critical temperature is more. Actual temperature is 25 and this is minus 140. If we compare 25 and 140, 25 is high temperature. So you tell me the actual temperature is greater than critical temperature or less than critical temperature. It is greater than critical temperature because critical temperature is minus 140. So actual temperature of air is greater than critical temperature. If the temperature is greater than critical temperature, it is gas. Why? Because critical temperature is minus 140, it is extremely low. But actual temperature of air in the atmosphere is 25 degrees centigrade, which is greater than critical temperature. It is gas. So air is gas under atmospheric conditions. I am talking about atmospheric conditions. Why atmospheric conditions? Please remember, right now I said atmospheric air. Because air may be in liquid condition. Remember, liquid air is there, liquid oxygen is there, liquid nitrogen is there. Generally in hospitals, if you see the containers, they will be supplying oxygen. In ICUs, they will be supplying oxygen, but that is in liquid condition. That is liquid condition, liquid air. So air or oxygen, it will be in liquid condition. It may be in liquid plus vapor condition. It may be in vapor condition. It may be in gas condition. But under atmospheric conditions, air is gas. That's what I am telling. Air is gas. Similarly, if you check each and every substance, I said substance. I didn't say it is gas. But after comparing the values, if you compare the values, we can conclude that it is an gas. Air is a gas. Right. Similarly, for other substances, if you check, the critical temperatures are extremely low compared to actual temperature. What about other substances, actual temperature? Just now we discussed. If air is 25, nitrogen is also 25. Oxygen also 25. Each gas is at the same temperature. That means actual temperature for all the substances is 25. But critical temperatures are extremely low. So actual temperature is greater than critical temperature. So therefore, all these substances, I said substances, all these substances are gases under atmospheric conditions. Right, these are gases. So we have seen what is gas, what is vapor, and these are all gases only. Right. Next, ideal gas. Just now we have seen what is gas. Now ideal gas. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which there are no intermolecular forces. An ideal gas is a gas in which no intermolecular forces in which there are no intermolecular, there are no intermolecular forces. No intermolecular forces. This is extremely important. No intermolecular forces. So an ideal gas is a gas in which there are no intermolecular forces. Intermolecular forces. Intermolecular forces. What are intermolecular forces? Intermolecular forces means attractive forces or repulsive forces. Attractive forces or repulsive forces. These are called intermolecular forces. Let us see, suppose various substances, solid, liquid, gas. If you see, in solids you see the molecules move continuously, randomly they move in gas molecules. In liquid, some molecules may move in liquid. But solids you see, in solids atoms are closely packed, very closely packed. So here there are some forces between molecules. Suppose this is exerting some force like this, and this molecule or this atom is exerting force like this. So between molecules there are forces. Suppose this is one molecule or atom. This is exerting force on this. This is exerting force on this. At the same time, this molecule or atom is exerting force on this. So therefore, these are called intermolecular forces. This is exerting some force like this. This atom or molecule is exerting force like this. So there are forces between molecules. These are called intermolecular forces. Since in solid the atoms are very closely packed, intermolecular forces are very huge. In case of solid, intermolecular forces are very huge. In solids, intermolecular forces are very huge. In liquids, some of the molecules, actually there is some gap. Compared to solids, in liquids, there is some gap. There is some gap. Compared to solids, here there is some gap. So here also there are intermolecular forces. Between molecules there are intermolecular forces, but compared to solids, intermolecular forces are less here. But if you see gas molecules, continuously they move. Between molecules there is a huge distance. In gas molecules, this is one molecule, this is another molecule. So there is a huge distance between molecules in the gas. But solids, the distance is negligible. In solids, distance is negligible. Distance is negligible. In solids, the distance is negligible, very closely packed. Distance is negligible. But gases, you see, the distance is very huge. Between molecules, you see, the distance is very huge. Here, distance is very huge. Distance is very huge. Very, very high. But here, distance is negligible. Remember, if distance is negligible, very closely packed, distance is negligible, more intermolecular forces, huge intermolecular forces. Here, the distance is very large. Between molecules, the distance is very large. If the distance is very large, you see there is no, suppose here there is one molecule, there is another molecule here. The distance is very large. If the distances are very large, the molecules are separated by means of very large distance, no intermolecular forces. So that's why, but sometimes they may come very close to each other, but suddenly they change their positions. Intermolecular forces are negligible. Distance is very large. Intermolecular forces are negligible. Intermolecular forces. Intermolecular forces, negligible. In case of gases, intermolecular forces are negligible. Intermolecular forces are negligible means almost intermolecular forces are zero. If there are no intermolecular forces, gas is called ideal gas. An ideal gas is a gas in which there are no intermolecular forces, or intermolecular forces are negligible, or no intermolecular forces, then it is called ideal gas. So this is the just definition, ideal gas, just a definition, right? But actually, let us take some points from kinetic theory of gases. Just no definition we have seen, but actually how to substantiate. Let us see some points from kinetic theory of gases. From kinetic theory of gases, I am taking some points. Point number 1. The volume of gas molecules is negligible when compared to total volume of the container. I am going to give 2 points. First, let me give the points, then I will explain each point. Second point, the gas molecules do not exert any intermolecular forces. First point, the volume of gas molecules. The volume of gas molecules is negligible. The volume of gas molecules is negligible when compared to total volume of the container. When compared to total volume of the container. So point number 1. And let me give point number 2, then I will explain. Next point. The molecules, the gas molecules do not exert any intermolecular forces. The gas molecules do not exert any intermolecular forces. So 2 points have given. Let us discuss about these 2 points. First point. Okay. First we will be discussing this one, then we will be discussing this one. So suppose there is a container. This container volume, suppose 1 meter cube. This container, in 1 meter cube container, from kinetic theory of gases, whatever right now I am discussing, kinetic theory of gases, it is nothing but which describes the behavior of gas molecules. Kinetic theory is nothing but which describes about behavior of gas molecules. That is kinetic theory. So whatever I am giving from kinetic theory only. Actually there are 2.4 into 10 power 24 molecules in 1 meter cube. In 1 meter cube container, suppose this is 1 meter cube container. In this container, there are 2.4 into 10 power 24 number of molecules in 1 meter cube container. And each molecule, if you see the diameter of each molecule, single molecule diameter of a single molecule, it is 2 into 10 power minus 10 meters. This is diameter of each molecule. And these molecules are something like spheres. If you see gas molecules in the microscope, they are something like spheres. Volume of a sphere. What is volume of sphere? Volume of a sphere. Volume of sphere is 4/3 pi r cube. 4/3 pi r. R is radius. Radius is diameter by 2. What is diameter? Just now I have given. Diameter is 2 into 10 power minus 10 by 2. 2 into 10 power minus 10. This is diameter by 2 power 3. So this is volume of a single molecule. This is volume of a sphere, that is single molecule. That is single molecule. Volume of a single molecule. Each molecule is something like sphere, right? Here 2 is cancelled out. And pi value is 3.14. For rough calculations, 3 and pi cancelled out. Rough calculations. So this is 4 into 10 power minus 10 power 3, 10 power minus 30. 4 into 10 power minus 30. Meter cube. And this is volume of a single molecule. Volume of a single molecule. But actually there are how many molecules? There are 2.4 into 10 power 24 number of molecules are present. So total, let us calculate total volume of container. What is total volume of container? Total volume of molecules. Total volume of molecules, that is 2.4 into 10 power 24 into 4 into 10 power minus 30. Total number of molecules into each molecule volume, 4 into 10 power minus 30. If you calculate this one, roughly you get 10 power minus 5. It is rough calculation. It is rough calculation. You get roughly 10 power minus 10 power minus 5. 10 power minus 5 means it is 0.00001. This is 0.00001 meter cube. What is this one? Total volume of molecules. What is total volume of molecules? What is total volume of molecules? Total volume of molecules. Whatever the molecules are present in the container, total volume of molecules is 0.00001. That is total volume of molecules. But actually container volume. What is container volume? Container volume is 1 meter cube. And total volume of the molecules is 0.00 something. If we compare total volume of molecules and container volume is 1 meter cube. Total volume of molecules is 0.00 something. If we compare both total volume of the container and volume of molecules, which is more and which is less? 1 meter cube, it is very more. It is a huge value. Compared to this value, 0.001 is very huge. That means the volume of molecules is negligible. Though there are so many number of molecules, huge number of molecules, 2.4 into 10 power 24 molecules, but the volume of molecules is negligible. The volume of all these molecules is negligible. What is the first point we have written? You read this point. The volume of gas molecules is negligible when compared to total volume of the container. What does it represent? What it represents? Let us see. First point, what it represents? Physically, mathematically we have calculated, but physically what it represents? Physically, what it represents? It represents there is a lot of free space here. There is a lot of free space. So molecules volume is negligible compared to this container. The volume of molecules is negligible means there is a lot of free space, lot of free space, lot of free space, free space. Free space is there. So that is the physical meaning. Lot of free space is there. If there is free space, gas molecules move continuously. But in solids, atoms are very closely packed. There is no space, free space. But in containers or in the atmosphere, a lot of free space is there. So gas molecules move continuously. When gas molecules move continuously, since there is a lot of free space, gas molecules move continuously. And the distance between molecules is very huge. The distance between molecules is very large. If the distance between molecules is very huge, intermolecular forces are very less. Just now we have seen, if distance is very huge, intermolecular forces are very less. If intermolecular forces are very less or intermolecular forces are negligible, the gas behaves as ideal gas. The gas behaves as ideal gas. So here a lot of free space is there, gas molecules move continuously, there is a huge distance between molecules. If there is huge distance between molecules, intermolecular forces will decrease. If intermolecular forces are decreasing, the gas behaves as ideal gas. Read the second point. The gas molecules do not exert any intermolecular forces. Why they don't exert intermolecular forces? Because distance is very huge. Since the distance between molecules is very large, intermolecular forces will be decreasing, thereby that is no intermolecular forces, then the gas behaves as ideal gas. Just now we have seen what is ideal gas. An ideal gas is a gas in which there are no intermolecular forces, right? So we have seen what is gas, what is ideal gas, and why we can call a gas is ideal gas. Because of these reasons, the gas, we can call it as ideal gas. Ideal gas means no intermolecular forces, right? So since the distance is very huge, intermolecular forces are very less, gas behaves as ideal gas, right? This is from kinetic theory. Everything, each diameter, all these things I have taken from kinetic theory only. So these are all practical values. These are all practical data from the kinetic theory of gases. So when a gas behaves as ideal gas, we have seen gas, what is vapor, and what is ideal gas. And from kinetic theory of gases, we have seen when means why we can say gas is ideal gas, we have seen. Now when a gas behaves as ideal gas, any gas can behave as ideal gas under low pressure or at high temperature. Under low pressure or at high temperature, we can treat the gas as ideal gas. Under low pressure, or under high temperature, under low pressure, gas behaves as ideal gas, or under high temperature, the gas behaves as ideal gas. So let us discuss why under low pressure and high temperature the gas behaves as ideal gas. Now we will be discussing. Let's take a small break, 2 minutes break, then we will continue.
Hello everyone, my name is Karthikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESC 2021. I have been associated with ACE Engineering. I have taken various programs like Lives, main classes, postal study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also like to highlight that in test series, I have given various mock tests which have helped me in the time of real exam, and in interview guidance program, building confidence in front of interview panel. It has helped me in my success.
Myself Abhishek Kumar Sharma. I have scored All India Rank 1 in UPSC Engineering Services Examination 2021 in Electrical Engineering discipline. Now I divide my preparation strategy into three basic things. The first thing is that you have to complete your syllabus from a basic standard source. The second thing is that you have to attempt previous year question. The third thing aspirant has to do is to solve as many test series as possible. I made 2 to 3 pages short notes of each and every subject. Now 2 to 3 pages short notes help in quick revision. If you keep working hard, you will definitely get success in this examination. This is what I followed, and I wish all the best for all the future aspirants. Thank you.
My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi, and I have secured All India Rank 1 in ESE 2021 from E&T branch. I took ACE Postal Course, Mains Test Series and Interview Guidance Program in ESE 2020 and ESE 2021.
Hello everyone, my name is Kartikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESE 2021. I have been associated with ACE Engineering. I have taken various programs like Life's main classes, Postal Study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also like to highlight that in test series, I have given various mock tests which have helped me in the time of real exam, and in interview guidance program, building confidence in front of interview panel. It has helped me in my success.
Myself, Abhishek Kumar Sharma. I have scored all India.
Now let us continue the session. Just now we have seen under low pressure, I said under low pressure or under high temperature, gas, any gas behaves as ideal gas. Now let us take first one, under low pressure. Suppose there is a gas. Suppose there is a piston cylinder, there is a gas here. Suppose there is a gas. These are suppose gas molecules. Suppose these are gas molecules. Something like this. These are gas molecules. Initially, this is the volume of the gas. Suppose it is expanding. The gas is expanding. Suppose finally, because of expansion, so the piston is right. Initially, the piston is here because of expansion. So right now the piston is here. This is initial volume of the gas and this is the final volume of the gas. Let us say, so now the molecules are something like this. Initially, they're very close. They are very close to each other. As the gas is expanding, now the distance between molecules is also increasing. You remember, whenever you say the gas is expanding, it is nothing but the distance between molecules is increasing. Whenever we say gas is compressed, the distance between molecules decreases. When gas expands, the distance between molecules is increasing. So just now I said it is expansion. Because of expansion, the distance between molecules is increasing. If the distance is increasing, just now we have seen. So right, initially suppose this is the distance. Initially suppose this is the distance, but right now this is the distance between molecules. Right now, this is the distance between molecules. As the distance increases, we have seen intermolecular forces decreases. As the distance is increasing, intermolecular forces will decrease. As the intermolecular forces are decreasing, you see, as the distance is increasing, no intermolecular forces will decrease, there are no intermolecular forces. So, if there are no intermolecular forces, the gas behaves as ideal gas. I told just now. An ideal gas is a gas in which there are no intermolecular forces. During expansion, pressure decreases. During expansion, pressure decreases. So as the gas is expanding, the pressure is decreasing. As the gas is expanding, pressure is decreasing. So under low pressure, right now the pressure is low. Pressure is decreasing means because of expansion, pressure decreases. So when the pressure is decreasing, that is nothing but pressure. So volume is increasing, pressure decreases. Generally, during expansion, pressure of gas decreases, volume increases. So volume increases means volume is increasing. Volume increases means the distance between molecules is increasing. As the distance is increasing, intermolecular forces will decrease. If intermolecular forces are decreasing and if intermolecular forces are negligible, the gas behaves as ideal gas, right? Under low pressure, gas behaves as ideal gas, number one. Number two, at high temperature. Suppose if heat is added. Suppose if heat is added to the gas. Heat. Suppose if heat is added to the gas, what happens? Due to heat addition, again molecules will start moving. Again molecules will expand. So expansion takes place. Again expansion, the molecules are separated by large distance. Volume increases. Large distances. Again molecules are separated by large distances. When molecules are separated by large distances, intermolecular forces will decrease. If intermolecular forces are negligible, gas behaves as ideal gas. So if you add heat, temperature increases here. If heat is added, the temperature also increases. So at higher temperature means I will explain once again. But right now, just now I said under low pressure and high temperature. But high temperature means there is a condition. Low pressure means there is a condition. What is the condition? I will tell. But under low pressure, gas behaves as ideal gas. And also at high temperature, gas behaves as ideal gas. Now listen, right? Just now I have given critical pressure and critical temperature values for various substances. So these values I already have given. Now listen carefully. Suppose if you take air, what is a temperature of air in the atmosphere? The temperature of air in the atmosphere is roughly, I said 25 degrees centigrade. And what is the pressure of air in the atmosphere? So we are saying atmospheric pressure. We are saying atmospheric pressure is 101.325 kilopascals. But what is atmospheric pressure? We are saying 101.325 kilopascal. What it represents? This value represents what? Pressure of air only. Air is a gas. Pressure exerted by the air in the atmosphere. Pressure of air molecules. Air molecules are exerting some force. That force exerted by molecules per unit area, that is pressure. So atmospheric pressure is 101.325 kilopascal means air molecules exerting some pressure. So atmospheric pressure means air only, pressure of air only in the atmosphere. Atmospheric pressure of air only, it is 101.325 kilopascals. Roughly it is 100 kilopascal. Roughly I said. Roughly it is 100 kilopascal. Temperature of air roughly 25. Pressure of air in the atmosphere is roughly 100 kilopascal. But actually what is critical temperature of air? Just now we have seen. Critical temperature of air. Critical temperature of air is minus 140 degrees centigrade. And what is critical pressure of air? Critical pressure of air is 3700 kilopascals. And if you check these two, actual temperature and critical temperature. Yeah, already we have checked. This is actual temperature, this is critical temperature, which is more? Minus 1, just now we have seen, this is minus 140, this is 3700 kilopascal. So, minus 140, it is very, very low temperature. Compared to this critical temperature, actual temperature of air, 25, is high temperature. High temperature means, look at this value. Compared to this critical value, critical temperature, it is high. High means it is not 2000, it is not 5000, it is not 10,000. Please observe the values. High means compared to critical, it is high. High temperature means compared to critical, it is high. At higher temperature, just now we have seen, gas behaves as ideal gas. And that is number two. Number one, under low pressure, you see, this is 100 kilopascal, this is 100 kilopascal, and this is 3700 kilopascal. 100 kilopascal I am not saying it is low pressure. But what is critical pressure? 3700s. Compared to 3700s, 100 kilopascal is low pressure. So actually in the atmosphere, pressure of air is 100 roughly. So which is low pressure? Compared to critical, it is low. That means it is low pressure. Air is under low pressure. Under low pressure, gas behaves as ideal gas. So under low pressure, actually the pressure is low compared to critical, and actually the temperature is high compared to critical. So therefore, at low pressure, gas behaves as ideal gas. Under high temperature, gas behaves as ideal gas. So for air, it is under low pressure, high temperature. Therefore, in the atmosphere, air, examples of ideal gases. Air behaves as ideal gas. Similarly, if you check other gases, the temperatures are very, other gases also, the temperatures are very less, the pressures are, temperatures are very less, and pressures also, compared to critical pressure, pressures are so low, and critical temperatures also low. So therefore, the temperatures, the critical temperatures are low. The actual temperature, just now I said, oxygen, nitrogen, each gas is at 25 degrees centigrade. That is, actual temperature is high because critical temperatures are low. And similarly for pressures also, it will be low pressure only. Just now for air I said it is 100 kilopascal, which is less than critical pressure. For other gases also pressure will be low only. So therefore, under low pressure and high temperature, the gas behaves as ideal gas. Examples, air is example of ideal gas. Similarly, oxygen, nitrogen, all these gases behave as ideal gases. Air, oxygen, nitrogen, hydrogen, helium, argon, CO2, all these gases behave as ideal gases. Suppose gate examination, suppose oxygen gas is given in the problem, which can be treated as ideal gas. Suppose nitrogen is given, can be treated as ideal gas. Air is given, can be treated as ideal gas. Any exam, gate exam, engineering service examination, any public sector examination, when these gases are given, they can be treated as ideal gas. Maximum number of times, they only tell, in examination problems only they tell, suppose air is given in the container, which can be treated as ideal gas. In the problem itself, they will mention. Suppose even it is not mentioned, it is treated to be ideal gas. So these are all examples of ideal gases. It's perfect gas. What is perfect gas? Perfect gas is an ideal gas in which the variation of specific heats, that is specific heat at constant pressure and specific heat at constant volume, or the variation of specific heats with respect to temperature is negligible. Perfect gas is an ideal gas. It is an ideal gas. It is an ideal gas. Perfect gas is an ideal gas in which the variation of specific heats variation of specific heats variation of specific heats variation of specific heats with respect to temperature variation of specific heat with respect to temperature is negligible. So this is definition of perfect gas. Perfect gas is an ideal gas in which the variation of specific heats, here specific heat means Cp and Cv. Specific heat means Cp and also Cv. Specific heat at constant pressure, specific heat at constant pressure. Variation of specific heat, that is Cp, Cv, with respect to temperature is negligible. Let us see. This is the definition. Let us see. Suppose I am taking air. Now I am going to give various temperatures, and what is Cp value, what is Cv value for air only I am going to give. For air I am going to give. Practical values I am going to give. For examination point of view, no need to remember. Just for idea, I am giving values. Suppose temperature minus 23 degrees centigrade, 27 degrees centigrade, 77 degrees centigrade, 127 degrees centigrade, and 177 degrees centigrade. These are various temperatures. And corresponding to these temperatures, Cp value, specific heat at constant pressure, for air only. At minus 23, it is 1.003. and at 27, 1.005. Similarly here, 1.008, 1.013, 1.020. These are Cp values of air at various temperatures. Similarly, Cv, 0.716, 0.718, 0.721, 0.726, 0.733. So these are practical values of Cp and Cv corresponding to various temperatures for air only. These values valid for air only, practical values, right? If you observe these values, if you check the temperature difference, if you check 27 minus 23, the temperature difference is delta T, temperature difference is 50 degrees centigrade. And similarly 77, 27, 50 degrees centigrade. 127, 77, temperature difference is 50 degrees centigrade. 177 and 27, the temperature difference is 50 degrees centigrade. The temperature difference is 50 degrees centigrade. It is temperature difference, 50 degrees centigrade, right? Check the Cp difference, 1.005 and 1.003. What is the Cp difference? 0.002. The Cp value difference, if you check, it is 0.002. 1.005 minus 1.003. Similarly, if you check the Cv value differences, 0.718 minus 0.716. The Cv difference also 0.002. So what is our observation? Check the variation. This is variation of temperature, 50 degrees centigrade. If you increase the gas temperature 50 degrees centigrade, how much Cp is increasing? Just 1.002. How much Cv is increasing? Just 1.002. Or it may be 003. It may be 003 or it may be 005. But 003 or 005, which is negligible. With respect to temperature variation, the variation of Cp and Cv with respect to temperature, compared to temperature, the Cp-Cv variation negligible. 0.00 means almost negligible. Cp-Cv variation is negligible. So if the variation of Cp-Cv is negligible with respect to temperature, this is called perfect gas. Perfect gas is an ideal gas only. Sometimes in examination problems they say perfect gas. What is perfect gas? Perfect gas is an ideal gas only. The variation of Cp-Cv with respect to temperature is negligible. Practically, it is observed practically. So since the Cp-Cv variation is negligible, Cp-Cv are treated to be constants. Cp 0.002, variation is negligible. So that means delta Cp is almost 0. If delta Cp is almost 0, Cp is constant. Similarly, delta Cv almost 0, therefore Cv is also constant. Cp is constant, Cv is constant. Cp, Cv are constants. They tell in the problems, GATE and engineering services, constant specific heat analysis. They tell constant specific heat analysis. Constant specific heat analysis means Cp constant, Cv constant, which is perfect gas analysis. Cp variation negligible, therefore Cp, Cv constant. So constant specific heat analysis means perfect gas. Perfect gas is nothing but ideal gas only. Perfect gas is an ideal gas only. Perfect gas is an ideal gas in which variation of Cp, Cv is negligible with respect to temperature. So practically the variation is negligible. Practically the variation of Cp, Cv with respect to temperature is negligible. So that's why it's a perfect, air is perfect gas. Air is perfect gas. And since the variation is negligible, throughout the syllabus, for air, Cp is 1.005 is taken. And throughout the syllabus, Cv is taken 0.718. Whether it is GATE exam or engineering service examination or any examination in thermodynamics point of view, for whenever air is given for calculation of air, always CP is taken 1.005 and CV is taken 0.718, which is corresponding to 27 degrees centigrade. And this 27 temperature is room temperature. 27 is room temperature. Corresponding to room temperature, CP, CV are taken. So this is perfect gas. The variation is negligible. That's why everywhere we take CP 1.005, CV 0.78 for simplicity of the subject. But actually, each temperature there is CP value, there is CV value. No need to consider. If you start taking CP, CV according to the given temperature, the analysis will be complex. It is very difficult to calculate each and everything. So that is the reason for whatever may be the temperature, we consider the values of CP, CV at room temperature 27 degrees centigrade for the simplicity of the subject. So this is perfect gas. What is perfect gas? It is an ideal gas only. But the variation is negligible practically. So that's why we treat the CP, CV constants. This is also called constant specific heat analysis. So this is perfect gas. So we have seen what is working fluid, what are the examples of working fluid, what is difference between gas and vapor, what is ideal gas, and from kinetic theory of gases I have given some points. And when a gas behaves as ideal gas, that is under low pressure, high temperature, and what is perfect gas, under what conditions the gas behaves as a perfect gas, and examples of perfect gas. Air is perfect gas. Similarly, other gases also almost same perfect gases. So that's all for today. And this concept is extremely important, which will be useful for GATE and engineering service examination, because 80% of the thermodynamic syllabus is ideal gas only. And this is ideal gas. Exactly. What is ideal gas? Why ideal gas? Intermolecular forces, everything we have discussed. So this concept, I hope it will be useful for you. Thank you so much. Okay, all the best.
Hello everyone, my name is Kartikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE online.